All right, in this video, we're going to talk some more about molecular orbitals. We're going to start with B2. But before we get to B2, I got to tell you one thing that's really cool. I was outside yesterday, and my neighbors have a couple ponds. Saw a bunch of geese fly away from the pond, and then I saw a bald eagle chasing one of the geese. It was awesome. It flew away, couldn't see it. They flew back. Goose landed in the pond. Eagle hovered over it for a couple minutes, or a couple seconds rather, and then it decided it could get it and kept flying. But it was really cool. That goose was flying as fast as I've ever seen anything fly. All right, B2. Now we have 2p orbitals, so leave yourself a little room here because it's going to get a little bit lengthy. B2 here. And B. I hope you guys are able to get outside and go for a walk and stuff. Don't just sit inside and do nothing. That would be very sad. Of course, you're not doing nothing. You're doing chemistry work, right? Lots and lots of chemistry studying. Forgetting all about your other classes. I'm kidding. I actually do not want you to do that. All right. So here's a setup for B2. Now we have those 2p electrons. Okay. And I probably did not leave myself enough room. So I'm just going to go ahead and erase these guys up here. And you might want to do that too. Of course, you're not probably using a tablet. But anyway, we're going to have our same orbitals here. And I'm just going to compress them a little bit just so I can fit in everything. So we have our sigma 2s and our sigma star 2s. Now, next what we have are 2 pi 2p, and don't worry about where this comes from, you just have to know the order. And then we have the sigma 2p, and then we have the pi star 2p, and then the sigma star 2p. So notice, I know that's a little sloppy, sorry, but that's a sigma star 2p at the very top there. Notice that this is kind of similar to what we did for hybrid atomic orbitals. So remember, we could have, from the p orbitals, we could have 2 pi bonds, and we could have 1 sigma bond, if you guys remember that. All right. So now here, this is where it's helpful, especially to kind of fill in where everything comes from. Okay, because the ones labeled 2p come from the 2p's. And the ones labeled 2s come from the 2s. So I do it like that. Some people do it a little differently. It doesn't really matter. And then if we look at the electron configuration for B2, it's 1s2, 2s2, 2p1. So then we just fill in the electrons. Again, leaving off the core electrons, but including valence. Okay, and I know you guys are all thinking, what kind of question is he going to ask? I can't really ask you to draw these on the exam because it's going to be on Blackboard. So I'm going to, basically what you're going to have to do is be able to draw one on your own and then answer a few questions about it. And I'm going to ask you to upload your work so you'll be able to show me what you did. All right. Okay, so there's all of our electrons. We have 6 electrons. And we just start at the bottom and we go up. We're using the same rules we always have to fill in electrons into orbitals. It's just now they're molecular orbitals. So 6 electrons. Here we go. 1, 2, 3, 4, 5, and 6. Now, why did those 2 electrons go on the pi 2p orbitals unpaired? Because that's how we add electrons to orbitals. They go unpaired when they can. And because those pi 2p electrons are degenerate, if you guys remember what degenerate means, they're the same energy level, they go unpaired when they can. And now, let me ask you something. Paramagnetic or diamagnetic? Paramagnetic or diamagnetic? This is paramagnetic. because we have unpaired electrons. Okay, and then our bond order. Like I said, we can do it a couple different ways. Let's just count them up. 1, 2, 3, 4 bonding electrons. 4 bonding minus 1, 2 anti-bonding. All divided by 2, that is equal to 1. Okay. So do we have a bond here? Yes, we have a bond order of 1, and so we would expect a sample of boron in the gas phase to exhibit diatomic boron, B2 essentially. All right, so be sure you know how to do that and understand where the bond order and the paramagnetic came from. Okay, let's move on. We're going to do carbon and do C2. And let's make some more room, because as you saw, this takes up some room. Okay, put in our 2Ps, 2P, 2S, and 2S. Alright, now everything falls out the same way. We have the sigma 2S, sigma star 2S. Then we have the pi 2P, and there's 2 of those. Sigma 2P. And then we have the pi star 2P. And the sigma star 2P. And something else to take note of here. Look, we have 6 total 2P orbitals. Okay, 1, 2, 3, 4, 5, 6. And how many orbitals came out of that? Molecular orbitals. Those are the atomic orbitals. How many molecular orbitals? 1, 2, 3, 4, 5, and 6. So the number of orbitals doesn't change. It's just their identity and their energy levels that change. Okay. And then, of course, we have the 2s. And we had 2 2s's, and we have 2 sigma 2s's. One's bonding, one's anti-bonding, of course. So let's throw in some electrons. Let's do sparkly electrons. Why not? I don't know why. But electron configuration for carbon: 1s2, 2s2, 2p2. Okay. So 1, 2, 3, and 4. 1, 2, 3, and 4. Now, again, we just start at the bottom and we fill in from the up to the top, and we have 8 total electrons. So 1, 2, 3, 4, 5, 6, 7, and 8. Okay. So now we can answer the same questions we've answered every single time. Paramagnetic or diamagnetic? Well, we only have paired electrons, so this is diamagnetic. Okay, and our bond order? Bond order: 1, 2, 3, 4, 5, and 6. Bonding minus 7, 1, 2 anti-bonding, all divided by 2, so that gives us a bond order of 2. So, if we have a sample of carbon, do we have a diatomic carbon? Absolutely. And what kind of bond does it have? It has a double bond. Okay, next video we'll finish out molecular orbitals.